Welcome to the concept of decision making. In the concept of decision making, one very important tool that we try to use in achieving the right kind of decision for any organization is called the decision tree. And any decision taken or the analysis of any problem through decision tree is called the decision tree analysis. What do we mean by decision tree? In simple words, decision tree is a very powerful decision making tool which can initiate a structured approach for this problem solving. That means we can have a easy chalked out diagram so that whoever is trying to gauge the problem easily understands it. It facilitates the evaluation and comparison of the various options and the results which are available to the organization, which is shown by the pictorial description of the decision tree. It helps the organization to choose the most competitive alternative. It is used widely as a technique for taking crucial managemential decisions like the project selection, cost management, operations management. We can easily say production method, and to deal with various kind of should I say strategic decision issues within an organization. In other words, if we can furthermore elaborate the concept of decision tree, as I said previously, we have talked about the importance of the graphical depiction of all the possibilities and the outcomes to solve a specific issue or to avail a potential opportunity. It basically gives the organization the visually facilities of the classification of the probable results in a very given scenario. If we can see here in this particular example that I have taken here, that initially it starts off with a situation, and the situation is the actual decision taken. That situation branches out into the choice nodes, the chance nodes, and the value nodes, which I have taken as different colors. Most importantly, joining those choice node, chance nodes, and value nodes are the branches, which is the key component of the decision tree. Now, let us get accustomed to different kind of terminologies or the terms that are being regularly used with decision tree. The first thing which we need to know is the root node. What do we mean by root node? Root node basically compiles the whole example. It is then divided into multiple sets which comprise of homogeneous variables. That means it's basically the starting point of the entire decision. The second term that we need to understand is the decision node, the subnode which diverges into further possibilities and can be denoted as a decision node. The third term that we need to understand here is the terminal node. That means it indicates to the final node, showing the outcome which cannot be categorized any further, which can be treated as the last value or the terminal value, through which the organization understands whether to take the right kind of decision. As I have earlier talked about the significance of the term branch, a branch denotes the various alternatives available with the decision tree, and most importantly, it connects different kind of should I say nodes to one another so that it can finally achieve the desired result. The two terms now that we will be talking about are the splitting and the pruning. What do we mean by splitting and pruning? Splitting is basically the division of the available options into multiple subnodes, which we have talked about in decision making. That means making from 1 to 2, 2 to 4. The options goes on bigger as the decision tree continues. And the exact reverse of splitting is called the pruning, where the decision maker needs to eliminate more than one or one subnode from a particular decision node. These are the terms that are frequently used with decision making. To understand easily what are the steps available or needs to be undertaken in decision tree analysis, this particular slide will help us understand those. The first step is understanding and specifying the problem area for which the decision making is required for the organization. That is what we call defining the decision making problem. The second step is to interpret and chalk out all the possible solutions to that particular issue which we have taken in decision making first step, and also look at their consequences at the given time. That is what we mean by drafting a decision tree with all possible outcomes. The third step is to present the variables on a decision tree along with respective probabilities values. This might happen as every single decision is a probabilistic decision. So every single decision, or the alternatives available to the organization, will also have certain probability attached to it. That's what we mean by putting in the relevant data with its probable values. The fourth step is to find out all the outcomes of all the variables and specify it on that decision tree that we have drawn previously. That is what we mean by determining and allocating payoffs for each possible outcome. Last but not the least is highly crucial and backs the entire overall analysis of this process. It involves calculating the expected monetary values of all the chance nodes, or what we say the options, and figure out the solution which provides the highest expected value, or which indicates towards the right decision being taken by the organization. That's the last step, or figuring out expected monetary value for every possibility. This, as I have shown it already in a directional way, that should be the ideal direction how a decision tree analysis should be completed. Let's consider one very easy example and let us try to understand how decision tree is drawn from this particular given example. Here, a person is a property consultant. He owns a shopping area in a shopping complex and has the options of either letting it out or giving it out as rent, or use it as completion of his own business. If he lets it out, then there is a possibility of getting a rent of 6 million which has a probability of 0.95, or receive zero rent which has the probability of the rest which is 0.05. If he puts it into his own use, he may generate a profit of rupees 5 million which has a probability of 0.6, or can have zero profit which has a probability of 0.4. So the decision is his to be taken. Now, as you can see here with the diagram, that particular box which I have started off indicates the decision which needs to be taken, and that particular decision is what Now it is being divided into two other options, which is either the person can let that particular place out or can conduct his own business through continuing in that particular area. Now, when he lets it out, there are two furthermore options which are available to him. Those are 6 million into that probability, which is of 0.95, and the rest is 0 profit into 0.05 probability. When he continues with his own business, he can either earn a profit of 5 million, which has a probability of 0.6, which I have multiplied, and the second probability is of 0.4 of earning 0 profit. Now, as you can say, and I have previously mentioned, to find out the expected monetary value, now the total expected monetary value from the option 1, we can easily find out it to be 0.95 into 6 plus 0.05 into 0, which gives us a grand total of rupees 5.7 million. Whereas the expected value of option 2, which is of continuing his own business, has a profit of 0.6 into 5 million plus 0.4 into 0, which gives us around the value of 3 million. Now, it is very easily understandable that higher the inflow is of the money, better the decision is. So that's why it is advisable for that particular property consultant to let it out or give that place out on rent which he owns to earn a higher profit. This is how a simple decision tree can be drawn, and this is a pretty easy example of actually how it is conducted. Moving on to another example of decision tree here. This is a 2-year project requires immediate investment of rupees 90,000. There is a 60% chance that the project may generate cash flow of rupees 60,000 in the first year. The other possibility of the first year is the cash flow of 50,000. The second year cash flows from the project are shown as below. If the cash flow of 60,000 is there in the second year, it might happen that the organization or the project may receive a cash flow of 70,000 with a probability of 80%, and the second probability of 20% is of a cash flow of 50,000. If the project receives a cash flow of 50,000 in the first year, the respective cash flows that the organization might get is a cash flow of 60,000 with a probability of 70%, and the other option is the 40,000 cash flow with a probability of 30%. Now, it is the organization's decision what should be done, keeping in mind the rate of return or the discount rate to be 10% per annum. This is the problem. In the next slide, we will be talking about how to solve this one. Moving on to the solution from the previous problem, what we had seen is the project requires an initial investment of 90,000. Now the actual decision what needs to be taken here is that whether this 90,000 needs to be invested or not. So that 90,000 comes in the decision node, and that 90,000 has two probabilities or two options available to it. The one, the organization can reject the entire project, or the organization accepts the entire project and invests 90,000. Now if the organization continues with the acceptance decision, that decision branches out to two furthermore decisions in the first year of 60,000 and 50,000, with a probability of 0.6 and 0.4 respectively. Moving on and continuing with should I say 60,000 node, the 60,000 node furthermore branches out into two more divisions. Those are 70,000 and 50,000 with a respective probability of 0.8 and 0.2, while the 50,000 decision branches out to two more further options, which are 60,000 and 40,000 with a probability of 0.7 and 0.3. Now if we see here carefully, I have drawn or I have written down P2, P3, P4 and P5. Those are the paths that we are talking about. How to indicate this particular path of P2? P2 is starting off with the 90,000, continuing with the 60,000 node and running it up to 70,000. That's what we mean by P2. P3 should be 90,000, 60,000 and 50,000 node. P4 should be 90,000 coming back to 50,000 and 60,000 node. And lastly, P5 should be 90,000, 50,000 and 40,000 node. And I have shown that exact thing below, where I have shown that path 2 is basically in year 0. Since it is an initial investment, that should be written in negative. That means 90,000, year 1 and year 2 respectively of 60,000 and 70,000. Here a newer concept is applicable, and that is the concept of joint probability. What do we mean by joint probability? That in any path, number of probabilities that comes in, to calculate the entire path's probability, we just need to multiply it. If there are two probabilities that are coming in between that particular path, that two probabilities will be multiplied, which I have done for every single path. If you look carefully at path P2, there are two probabilities which are 0.6 and 0.8. So those two's multiplication should give me a figure of 0.48. That should be the entire path 2's joint probability. Similarly, the joint probabilities of path 3, 4 and 5 are simultaneously 0.12, 0.28 and again 0.12. Coming back to the calculation part here, since all the values are not in similar kind of time zone, we need to calculate and bring it back to the similar kind of time zone. And what is that similar kind of time zone? Since it's a decision which needs to be taken in case of investment, all the values needs to be transferred into the present worth value. Now if we need to transfer the present worth value, one particular formula which we need to use is 1 divided by 1 plus I whole to the power n, which gives us the value of future worth which we can transfer it back into present worth. When we do that, the first year and second year values, I have shown it in one single path and I have completed the entire thing based on that only. If you can see in the expected NPV, I have written down the path in the first column. The second column is the year 0 value, which are same for everyone. Year 1 value coming back to the first year's value. If I continue on the path of 2, that means 60,000, which needs to be transferred into, should I say, the present value. That needs to be divided by simply 1.1. And very similarly for 2, the value should be 70 divided by 1.1 whole to the power 2. Very similarly for the first year, again we need to divide the entire value of 60, 60, 50 and 50 by 1.1, and year 2 we have to simultaneously divide it into back into 70, 50, 60 and 40, each divided by 1.1 whole to the power 2. Now what are if the values that we are getting here, what we have to do, add up the values of 0 column, first column and the second year's column. That means if you see for path 2, minus 90 plus 60 divided by 1.1 plus 70 divided by 1.1 whole to the power 2. If calculated correctly, that should give me the net present value of that particular path at 22.36 thousand. If that is the case that I am getting, then we need to multiply that particular NPV of 22.36 with the joint probability of the path which we have previously calculated at 0.48. If we do that, the expected present value of the entire path 2 goes back to 10.732, which is the actual value of that path. So here we understand how to calculate the expected net present value of a particular path. If you students go on calculating the values from path 3, 4 and 5, the values should give you 0.700, 1.4028 and in a negative 1.3812. If we add up all the values of the expected NPV of all the paths that are available to us, the entire project has an NPV which is of positive 11.455. So if the organization accepts the project, that should give at the end of second year a profit of 11,455 to the organization. Whereas if the organization rejects the project, the organization loses that similar amount of money. So from the decision tree, we have calculated that the project should be continued and the organization should go on with the 90,000 investment. Taking another example, for the following project, annual benefit is most likely to be 8,000 with a probability of 60%. There is a 30% probability that it will be 5,000 and the highest value is most likely to be 10,000. A project life of 6 years is twice as likely as a project life of 9 years. Assuming the initial cost of the project is 25,000 and the 10% given interest rate, we need to find out that whether the project is profitable or not, or the organization should continue investing in the project or not. This is a bit of tricky solution to have, but let's go into the solution here. From the previous problem, we have seen that the organization is opting for a project which has 3 different types of annual benefits with different kind of probabilities attached to it, and most importantly, the lifetime of those annual benefits vary from one time to another. So here, if we consider the annual benefit to be of 3 different values, which are 5,000, 8,000 and 10,000, the respective probabilities are 30%, 60% and 10%. Why 10? Because it has not been said that 10,000 will have a value or the probability value of 10%, but the rest too has been given to us, and we know that the entire probability always adds back to 1. So from there we can easily find out the remaining probability value to be 10%. Now what is interesting here, that the project life has been varied into 2 different lifetimes. What are the 2 different lifetimes? If we go back to the sum, it says a project life of 6 years is twice as likely as that of 9 years. So basically we can understand here that 5,000, 8,000 and 10,000 will run for a project lifetime of 6 years, the same annual benefit values will run one more time for 9 years. And what are the probability that the project runs for either 6 years or 9 years? Again, referring back to the sum, a project life of 6 years is twice as likely that of 9 years. So the probability of 6 years, the project life of 6 years, is twice the value than that of 9 years. So we can easily say, if we divide it, that 2 by 3 becomes the project lifetime of 6 years probability value, and 1 by 3 becomes the probability value of the project lifetime being 9 years. If we convert that 2 by 3 and 1 by 3 into decimal values, we generally get the values of probability of 66.7% and 33.3%. This is how the entire decision tree stands right now. If we move back now to the columns here, I have made the annual benefit column. The first probability refers to the annual benefits probability. The third column refers to the life of the project. The fourth column, or the second probability column, refers to the life's probability. And that too for each single path, as I have mentioned it in previous sums as well. The joint probability will be the two probabilities multiplied and taken the resultant value as the joint probability. Now, coming back to the calculation for the first annual benefit row here, if we take the annual benefit of 5,000 and the probability of 30% with a lifetime of 6 years, which also has a probability of 66%, so 66.7% into 30% gives us the joint probability of roughly 19.9, which I have converted back to 20%. Now, one single thing we need to consider here is the calculation of the present worth value. How to convert that particular present worth value? If you can go back and look at the workings of this particular sum, that if present worth value of 5,000 6 years is basically, there is an initial investment of 25,000 which is already at present worth, so that is negative 25,000, which has no transformation because it is a present to present transformation. If we add back the annual benefit, which is of 5,000, which we are getting for continuously 6 years, that means it is an annual value turned into present worth, given the interest rate of 10% and 6 years, we find out the value to be negative 3,244 or 24, or a loss of 3224. That's what I have put in the present worth column. So simultaneously, very similarly, we have to calculate the same value which we have done for 5,000 and 6 years, for 8,000 6 years, 10,000 6 years. And then if we multiply the present worth value with the joint probability, we get the value of the total NPV now, which is coming at negative 645 or a loss of minus 645. Very similarly, if we now go on continue for those two, 8,000 and 10,000 value, the net present value should come at 3937 and 1237. Now coming back to the second part of the annual benefit, here we have to be very careful in understanding that the years are changing. So when we will be calculating in our workings the present value of 5,000, 8,000 and 10,000 for the second time, this time around we need to check in and we need to calculate the present worth based on the years to be 9. If we successfully complete doing it as I have shown it in my workings as well, the entire net present value, if I am multiplying every single present worth with the joint probability, the entire net present value gives the organization a profit of 10,209, which is the end result of this entire decision tree problem. So the organization should be investing 25,000 regardless of the project running for 6 years or 9 years. The organization will earn a profit at the end of the period. So it is useless for the organization to reject the project.